Hello everyone. In this video we're going to extend the knowledge about wellbore stability to deviated wellbores. So far we have seen applicabilities of wellbore stability to vertical wellbores going from point 61 to 65, and we're going to see how that now applies to a deviated wellbore. First of all, we're going to start describing what is a deviated wellbore and how we can quantify that. The deviation of a wellbore can be quantified by the angles of azimuth and deviation of the wellbore. These two angles depend on the orientation of the wellbore. For this example, let us consider that the wellbore is being drilled in the direction northeast. So you can see that this blue line is going to represent the wellbore at a particular depth. This is going to be its orientation. It's going down, and in order to get from point A here to point B over there, we have to go north and east, and that's how we get to this point. And also, of course, we need to go down. So let's do that again. We go north, we go east, and finally go down with depth in order to get to this location at any point in the wellbore. And we can represent this three-dimensional orientation of the wellbore by these two angles. Again, these are the azimuth and deviation angles. Similar to what we have seen for the poles of faults, we're going to have two angles, and in this case, the azimuth angle is going to be the angle between the projection of the wellbore orientation on a horizontal plane, and the angle between this line and the north is going to be the azimuth angle, measured clockwise from the north towards the particular line that you are looking at. And the deviation angle is going to be the angle between vertical direction and the direction or orientation of the wellbore. For example, a deviation equal to 0 is a vertical wellbore. A deviation equal to 90 degrees, that means that that's a horizontal wellbore. This orientation, we can also plot it in a stereonet projection. In this stereonet projection, we see the orientation of the wellbore or the azimuth here by this angle denoted this time as delta. And also we can see what is the deviation of the wellbore. For example, for this particular orientation going the direction northeast, we would expect that this wellbore or this particular orientation would hit a lower hemisphere projection on a section which is at more or less at this location in the stereonet. This is going to be the angle of the azimuth of the orientation of the wellbore. And here we're going to have the deviation. A dot which is in the center would be a vertical wellbore. A dot which is on the periphery of this lower hemisphere projection is going to be a horizontal wellbore. For example, a dot somewhere over here is going to be a horizontal wellbore going direction north. A point somewhere over here will be a horizontal wellbore going in direction east. And anywhere in between, we will have a deviation which is neither a vertical nor a horizontal wellbore. So how do we map the deviations of wellbores in practice? We use what is called a deviation survey. And here I have one example of one of these files. These files are usually denoted by the extension .dev, meaning that this is a deviation survey of a wellbore. For example, in this case, we have the number of the unique well identifier number for that wellbore, UWI. We see the name of the block or the section where this wellbore is. Next, we have measured depth, true vertical depth, east-west offset, north-south offset, true vertical depth sub C, and the path of the wellbore in direction X and the path of the wellbore in direction Y. The path of the wellbore in direction X is going to be this axis, the east axis. The Y path or the Y axis is going to be the north axis. And the numbers that we have in here, we know what is measured depth and true vertical depth, right? Measured depth is along the wellbore, true vertical depth is just in vertical direction. And here we have the offsets for each incremental point. For example, here we measure the orientation of the wellbore going from a measured depth from 0 to 100 feet. In that interval, the wellbore went in direction east-west negative 32 feet and in direction north-south negative 0.12 feet. What that means is that the change has been, as you can see in this equation, so columns from A to K are the deviation survey file, and here I added in this spreadsheet also I added this equation just to show that change in direction east-west, or this east-west offset that we see over here, 0.32, is a change in direction in the x coordinate. So if I press enter, that 0.32 is the same as this 0.32. And what that means is that in this particular case, this wellbore going from 0 to 100 feet of measured depth, it went in negative direction. So that means it went in direction west. And similarly, if we look at the change in direction y, this one went in negative direction 0.12 feet, which means it went in direction south. And we can see all these changes on all these offsets at several points along the wellbore. This is what makes a deviation survey file and help us see what is the orientation in 3 dimensions of a wellbore as as measured depth increases. Here I have added one example. I made a plot of what is here the east-west and north-south offset of this particular wellbore. We see that it starts here at the center, and those offset, they change as the wellbore goes deeper and deeper. For example, the first point that we have in here, at a very shallow depth, it goes negative, it goes to the south, but then it starts to go north, and also tends to go to the east, more to the east. At some point, it changes direction, and it goes, continues going to the north, but now in direction east. And we can also summarize this deviation survey on this type of plots in which we use the same as before, the same lower hemisphere projection, and for each point we have calculated what is the angle of azimuth and what is the angle of deviation. In this example, we see that this wellbore starts deviated, and as it goes deeper and deeper, it gets centered around 0, so that means that it goes vertical. And this is going to be very useful, as we're going to see later on, because it's going to let us calculate wellbore stability as a function of these two angles, the azimuth angle and the deviation angle. Okay, so before getting into wellbores drilled in an arbitrary direction that are neither horizontal or vertical, let's first talk about horizontal wellbores, which are a little bit easier to understand as we go and talk about the wellbore, the stability of deviated wellbores. And for that, here I have made one example in which we have 3 wellbores, 2 wellbores. We have 3 directions, And these two wellbores start vertically, and at some point they deviate, and one deviates towards the east, and another one deviates towards the south. We're going to start analyzing what is the stability of the vertical and horizontal sections. And for this particular example, I have assumed also that we are under normal faulting conditions, and the orientation of the minimum principal horizontal stress goes in direction east-west, as you can see in this schematic. So let us first take a look at what would happen with a vertical wellbore. If you notice, a vertical wellbore in this example would have a cross section of the wellbore that would be on the plane number 1 according to the notation in this cube. In order to have a cross section of a vertical wellbore, we need a horizontal plane. In this case, this is a horizontal plane, the plane number 1. If we take a look at what would happen in a cross section in a vertical wellbore, this is what you would expect. And in this case, let me just show part of this drawing so you get your attention mostly on this section. In this particular cross section of the vertical part of the wellbore, and according to the stresses that we have assumed, their value and their orientation, on a normal faulting regime for a vertical wellbore, we would have in the cross section of the wellbore acting SH max and SH min. SH max is higher than SH min, therefore you would expect tensile fractures oriented in the direction of SH max. These are the tensile fractures, and you would expect breakouts if they occur in the direction opposite to the direction of the maximum principal stress, perpendicularly actually to that direction. So in this case, you would expect the breakouts to appear in orientations east and west, and the tensile fractures north and south. Because the minimum principal stress in this case is SH min, as these drilling induced tensile fractures occur, if they were to extend further into the formation, they will extend normally as planes which are perpendicular to the minimum principal stress. And these are these planes, which are perpendicular to SH min. All right, so far there is nothing new, but what you're going to see is that the same principle applies also to the horizontal wellbores. So let's take a look now at a wellbore which is going to be drilled in direction north-south. In this case, is going towards the south. And is this wellbore, and we'll take a cross section of this wellbore number 2. A cross section will be on a plane which is perpendicular to SH max. And for that case, this would be such plane. And in this case, we are going to have in the cross section of this in the cross section of this horizontal wellbore, we will have acting vertical stress and SH min. Notice that now we don't have SH max anymore because SH max is perpendicular to the screen. So let's go to that case. For such a horizontal wellbore, now these are the two stresses that we have to consider. Because this is normal faulting, the vertical stress is going to be higher than the horizontal stress. And if we, again, have drilling induced tensile fractures, those would align with the direction of the stress which is the greatest between these two. In this case is SV, so this is why these drilling induced tensile fractures would occur on top and bottom of the wellbore, and perpendicular to that we will have breakouts, and those would occur on the sides of the wellbore. And let's go finally to case number 3. One more thing about this case. Remember that if we had open mode fractures, hydraulic fractures, those will tend to be perpendicular to SH mean, and in this case we can see that for this particular wellbore, if we had these drilling induced tensile fractures which now are growing perpendicular to the paper, it's a plane that it's here is going in direction uh, vertically, it's in vertical direction, but it's also going in direction, in this case, north-south. This plane is perpendicular to SH mean, so if such fracture would continue growing further out from the wellbore, it would still be perpendicular to the minimum principal stress. So we would still fulfill the condition that this open mode tensile fracture would be perpendicular to the least principal stress, which in this case is SH mean. So far, we have seen how we apply this condition and the knowledge about tensile-induced fractures and breakouts to a horizontal wellbore. If you wanted to use, for example, the Kirsch equations to a horizontal wellbore, the only thing that you have to do is to replace the stresses for these two stresses. The largest one, which is SH max in a vertical wellbore, now will be replaced in this case by SV, and the lowest one, which in the case of a vertical wellbore is SH mean, in this case will still be SH mean. So the equation remains the same. The only thing that you change are the stresses, and you use the stresses that apply for a particular orientation of a horizontal wellbore. And let's see the last case now. This case, in this case, we have a wellbore which is going first vertical and then goes in horizontal direction towards the east. And we'll take a look at what would happen at the section of the wellbore which is horizontal and is going in the east direction, and the cross-section of such wellbore would lie on a plane which is perpendicular to SH mean, and this case will be this plane, plane number 3. We're going to do the same thing. We're going to try to find out where would tensile fractures occur around the wellbore and where would breakouts occur. And now the two stresses that we're going to consider are the vertical stress and the maximum horizontal stress. And this is going to be such cross-section, and in this cross-section we would expect tensile-induced fractures, these two lines, to be in the direction of the maximum stress for this particular plane. In this case, SV is larger than SH max, so that's why the tensile fractures occur on the top and bottom, and in perpendicular direction we have the breakouts. Okay, now notice something. For this particular case, we might have these tensile fractures which near the wellbore are oriented in a direction such that these tensile fractures are perpendicular to the local least principal stress. And in this case, the local least principal stress is the hoop stress. The hoop stress, which will go in this direction, near the wellbore, makes this tensile fracture to be oriented as this vertical plane, which is extending in the direction east-west. It's a vertical plane that goes in direction, we could say has a strike, which is direction east-west. But in this problem, we also know that the far field principal stress, SH mean, goes in direction east-west. And we know from hydraulic fracturing principles that a hydraulic fracture would tend to grow perpendicular to the minimum principal stress. So here we have a change in the orientation of the local principal stress. Locally near the wellbore, it's the hoop stress, and it goes in direction north-south. near the wellbore, because that's the least principal stress is going to be the hoop stress when tensile fractures occur. But as you go further away from the wellbore, far from the wellbore, the orientation of the least principal stress is east-west. So it goes from being north-south to being east-west. And because of that, you may expect that if a drilling-induced tensile fracture grows near this horizontal wellbore, as it goes further into the formation, this hydraulic fracture is going to turn in order to find the orientation of the least principal stress. And more or less, this is what the shape of what you would expect to find in such a hydraulic fracture. It would turn from being perpendicular to the direction north-south to be perpendicular to the direction east-west in this particular case. So if you, for example, are looking for applications of hydraulic fracturing and you wanted to extend a hydraulic fracture out of this wellbore into a formation, again for completion regions, probably this tortuosity is not good. In that case, what you may want to do, if you really wanted your fractures to have almost no tortuosity and to be more or less planar, what you will do is, instead of having in a scenario which is something like this, in which you have a tortuous fracture that may screen propant, you may want to have something closer to this. And in order to get something like that, what you would do is perforations around the wellbore that would allow you to find the best orientation of these stress concentrations such that your tensile fracture planes, like this one or this one, orient in the appropriate direction such that your hydraulic fractures continue growing on the plane of a tensile fracture. Okay, so coming back to wellbore stability, if we wanted to calculate the wellbore stability of such wellbore that starts vertical, then deviates and goes into horizontal direction, what we have to do is to evaluate the wellbore stability along all of these orientations. Notice that here the circle represents the wellbore in vertical direction, the star represents the wellbore in horizontal direction, and the triangle here, it represents the wellbore at a certain depth where the orientation is more or less, the deviation is more or less 45 degrees, and these dots represent the orientations at deviations that are in between these three conditions. Notice that it is very important that in this lower hemisphere projection, we do not plot the orientation that goes from surface to a particular point. It's not the orientation of a line that goes from here to there. It's the orientation at the local condition. So here, for example, is horizontal. That's why it's here. Here is vertical. That's why it's there. And notice that all these points, they follow the local orientation of the wellbore. They plot local conditions, not the secant values. So this is the tangent. Here you obtain the tangent of the orientation of the wellbore, which is not the same as a secant value, which we go from the origin to a particular point. All right, so here you have an explanation of how you would use how you would locate tensile fractures and breakouts in vertical wellbores and horizontal wellbores that are aligned with the principal stresses. In this case, notice that our principal stress is in going direction east-west, and so that we can simplify this problem for these horizontal wellbores whenever they are going into the directions of at least one of the principal stresses. And you can do the same with the Kirsch equations. Now you can use the Kirsch equations for these horizontal wellbores as long as they are aligned with one of the horizontal stresses. I'm going to ask you to be able to solve problems in which your horizontal wellbores are aligned with at least one of the principal stresses, because with those problems you can use the Kirsch equations that we have seen for vertical wellbores. You can extend that to a horizontal wellbore very easily. And here you have one example that problem 6-4 that I'll let you work on that on your own at home. It's similar to what we have seen before. What happens in the case that you do not have a wellbore which is aligned with the principal stresses? Well, in this case, what you have to do is you have to uh, do a little bit more of calculations, and those start by finding what is the coordinate system of the wellbore, which is going to be a function of the angles of azimuth and deviation. I'm not going to go into the details and the explanation of this calculation. If you're interested, I encourage you to look at my advanced geomechanic videos. But for my undergraduate class, this is not going to be included. You shouldn't know the details, but you should know just the generalities about what this computation takes, and that's what I'm going to explain right now. All right, so as I was saying, the first thing that you would do would be to find what is the local coordinate system of your wellbore. In this case, the first axis goes from the center to the lowest portion of the cross section of the wellbore. Your second axis goes from the center to a direction which is on a horizontal plane. And the third axis goes in the direction in which the wellbore is being drilled. In this example, the wellbore is drilled in direction northeast, and that's why the third axis is going in this direction down. You can try here the right-hand coordinate system rule, and you will see that if you point your index finger in direction of x, uh, your middle finger in direction y, your thumb finger direction z is going to be pointing down. All right, so once you have the azimuth and the deviation of the wellbore, you can build this matrix, which is going to be the matrix that is going to allow us to convert the geographical coordinate system into the wellbore coordinate system. And once you know what are the principal stresses at a given location, here given by the tensor SP, you're going to be able to convert the stresses, the principal stress at a given location, into the stresses in the orientation of the wellbore. And this is going to be very useful because after we have the orientations of, or actually we have the stresses in the coordinate system of the wellbore, we're going to be able to calculate what are the stresses around the wall of the wellbore for a cross section of the wellbore. So similar as we did with the Kirsch equations, we're going to compute what is the radial stress, what is the tangential stress or hoop stress, what is the stress in direction of the wellbore in the axial direction, but we are also going to have in this case an additional term, which is a shear term in the direction theta z. And this shear stress shows up because now the direction of our wellbore, here given by the axis x, y, and zb, is not aligned with the direction of the principal stresses, here given as x1, x2, and x3. Whenever that happens, we're going to have a shear stress around the wellbore in direction theta z, that means on plane which is perpendicular to theta and in direction z, and also therefore there is going to be a shear stress tau z theta, which is not going to be zero, and is going to be given by the off-diagonal components of the stress tensor S23 and S13. you can extend the Kirsch equations in order to have this component. And after you do that, because having this additional uh, shear stress is going to turn out that our local principal stresses are not going to be necessarily aligned with direction of the wellbore and the axis of the wellbore and the tangential direction. Now we're going to have to calculate what are the principal stresses at that particular point, and those are going to have values which are not equal to the values of the hoop stress and the axial stress. And once we find those maximum and minimum values for the local principal stress, we're going to be able to tell whether there is shear failure or whether there is tensile failure. The procedure is very similar to what we have seen for a vertical wellbore, but now we have to do this additional step to compute what are the local stresses around the wellbore. And then we apply the failure criteria, shear and tensile strength, and we're going to be able to calculate breakouts and tensile fractures. Notice that here also, because the presence of a shear stress tau theta c, there's going to be an angle here, and that angle is going to represent the misalignment between the principal stresses and the direction of the wellbore. All right, so once we do all of these, we're going to be able to compute breakouts and tensile fractures the same as we have done for vertical wellbores. And it's very useful now that in order to analyze all the possible orientations of a deviated wellbore, we're going to consider these plots of half hemisphere projections. So all of these plots, let me show what they are. All those circles are what we were seeing here. It's a half hemisphere projection where a point in that circle represents a particular orientation of the wellbore. So keep this plot in mind. Remember, north, west, east, south, vertical wellbores, and on the periphery, horizontal wellbores. Now we take that to this example. Here, I show an example of the calculation of the unconfined compressive strength of the rock required for a given state of stress that we see in this plot and for a given condition of pressure in the wellbore and pore pressure and values of principal stresses. Here we see what is the strength of the rock, the shear strength of the rock required in order to have a stable wellbore. All right, so let me explain a little bit what this plot is showing. In this example, we have a strike slip case. The maximum principal stress is oriented about 20 degrees from the east towards the north. This is S1. The least principal stress is perpendicular to the direction of S1. So this is SH min and this is SH max. Let's first think in terms of vertical wellbores and horizontal wellbores. For a strike slip state of stress, the maximum difference in stresses is going to occur between SH max and SH min. And therefore, the plane or cross-section of a wellbore with maximum stress anisotropy is going to be a plane that combines these two stresses, S1 and S3. Let me draw that in order to help in trying to depict what I'm saying. In this case, we have SH max going in this direction, SH min going perpendicular to SH max, And in this case, this is a strike slip. Therefore, the highest stress is SH max, intermediate is SV, and the least principal stress is SH min. The wellbore which is going to have the highest difference in stresses is going to be, in this particular case, a vertical wellbore, because it's the orientation that combines the maximum difference between stresses SH max and SH min. That's why in this particular plot we see that the warmest region, and that's the region that requires the highest unconfined compressive strain in the rock, is for a vertical wellbore, which locates near the center. This is a wellbore that will require the maximum strength in the rock because it's the orientation at which I have the maximum difference between SH max and SH min. In this particular example, we also see that a horizontal wellbore drilled in direction of SH max will be a wellbore somewhere over here or over there, is the wellbore that requires the lowest strength in the rock, in this case about 80 MPa. And that's because that particular wellbore, in this case horizontal, going in the direction of SH max, has the lowest difference between stresses. In this case, we would have a horizontal wellbore that combines SH max and SV. And in this particular case, we see that the required unconfined compressive strain is about 80 MPa. And that would be for now a horizontal wellbore going in this direction. And the intermediate case would be a horizontal wellbore going in the direction of the minimum principal stress. In this case, it combines vertical stress and the direction of SH max. Okay, wait a minute. So a wellbore, let me say this again. A wellbore that goes in direction of S1 is going to combine the stresses of the vertical stress S2 and SH min. Small mistake in here. Fortunately, I caught that on time. This should be the wellbore that goes in the direction of SH max and requires an unconfined compressive strength of 80 MPa. And a wellbore that goes in the direction of the minimum principal stress, in this case, is a wellbore that combines now SH max and SV. This is going to be the horizontal well that goes in the direction of SH min, and in that case the UCS appears to be required to be more or less, I would say, 170 MPa. And the vertical wellbore, let's finish this example. The vertical wellbore that occupies the direction, let me do it with brown, between these two, SH max and SH min, that's going to be a vertical wellbore and requires, in this case, a UCS of about, let's say, 200 MPa. By the way, that would be quite a strong rock. Okay, so this is how we would use these plots. And all the intermediate cases between horizontal around here, horizontal in the direction of principal stresses here and there, and vertical, the cases that we have seen, using the equations that I showed above, you can compute what would be the required strength of the rock at any deviation, at any azimuth of the wellbore. And we can extend this if we're talking about breakouts also to compute, for example, what would be the breakout angle for a particular wellbore and considering a particular mode of failure of the rock. This is just a type of failure uh, equation of the rock. And in this example, we can see that we would expect, for example, for a given pressure in the wellbore, a wellbore breakout with a given angle, and we would expect, similarly to what we saw before, a large breakout angle here in the order of 40 degrees for either a vertical wellbore or a wellbore drill in the direction of SH mean, or we could have almost no breakouts here equal to 0 for wellbores which are drilled near the horizontal direction in the direction of the maximum principal stress. And we can apply the same procedure. This case is strike slip. Here I have another example for, in this case is, let's see, it's normal faulting. In this case, the worst direction or the most compromised direction to drill a wellbore will be, instead of a vertical wellbore now, is a horizontal wellbore, because that's the wellbore that combines the maximum principal stress SV and the minimum principal stress SH mean. You can do that also for reverse faulting. The same principle applies. And you can also do that for tensile fractures and compute what would be the likelihood of having tensile fractures for a given orientation. It's all done with the same equation that we have seen for vertical wellbores. It just has to be extended for an orientation which is not aligned with one of the principal stresses. But if you use those equations, you could do that. What I'm going to ask you to know is how to interpret these plots and how to interpret what is the azimuth and what is the deviation of a wellbore in some of these plots. As we were saying before, if, for example, I would take this particular solution for a given case, let me actually copy the one from the one I was working with before. I could use this let me try another trick in order to get this image. At a given location, I could compute this solution, and let me paste this over here, and I could use now this particular solution that I have in combination with my deviation survey file. And let's say that I have, for example, a wellbore that goes into starts vertical over here and goes into the direction of minimum principal stress for fracturing. So in this case, the minimum principal stress would be this one. So that would be a wellbore that starts vertical and goes into its final orientation to be here horizontal. And as it goes from vertical to horizontal, it's going to go through this path in the orientation. And this plot is going to help me see what are the wellbore stability requirements for such wellbore to go from vertical to horizontal. In this example, I'm showing what is going to be for example, the strength of the rock required for that wellbore to not to develop any shear fractures, but similar as what we saw before, we could have plots for breakout angle or for knowing if there are tensile fractures or not. And by superimposing the deviation survey with the particular uh, computation of wellbore stability, we can tell then what is going to be the path of such wellbore. Notice something. If, for example, you were to drill a wellbore in this direction, going in the direction of the maximum principal stress, like over here, it would go from having breakouts to not having any breakouts at all as it goes horizontal. So here, it will be no breakouts. Okay, so with this example, we finish the discussion of deviated wellbores. Again, if you want to know in detail about how to do these computations, I encourage you to see my advanced geomechanics videos.